Unreal Engine has a number of pre-made mechanisms that help you split the frequency spectrum of a sound into different bands to be analysed. These all act upon a submix. You may remember that in the central village of the demonstration level, that's bookmark key 1, there's a tavern where the villagers go to put the world to rights over foaming jugs of pumpkin cider. Let's have another listen to the music that's playing inside the tavern and focus on the fireflies that are dancing around the lantern outside. You'll notice that the fireflies are actually changing colour and are doing so in time with the changes in the music. This is achieved through analysing different frequency bands of the submix to which the music is assigned. This isn't hugely complicated, so let's delete the existing system so that you can follow how to build it up from scratch. Firstly, we check whether the player has spawned already overlapping with the collision sphere in the blueprint, and that calls this custom event here. Or if the player overlaps with that sphere, we want either of these two events to trigger our system. So we'll create a custom event here, and we'll call that start. And we'll create a function here to trigger that custom event. The approach to frequency analysis that we're looking at in this video is the analysis of any audio that's playing back on a specific submix. So if we find our music here, you can see that that is assigned to this submix called tavern music. Back in our blueprint, we've created a submix variable and we've assigned that tavern music here. If you wanted to analyze all the audio that's going on in a game, you could choose to look at the master submix. So now we've got that submix that the music's being played on, we can drag out and add a spectral analysis delegate. This allows us to define some settings, and we can drag out here and create a custom event or delegate that will give us the magnitudes of audio within the frequency bands that we define. So we create another custom event, we'll call this one bands. We'll just set this noise floor to -80 for now. I'll come back a bit later and talk about that a bit more. We then need to start spectral analysis on this submix. So we connect that up. And when we leave that collision sphere, we need to stop spectral analysis. This start spectral analysis node gives us various options as to how the fast Fourier transform based analysis should be done. For our purposes here, we'll just leave it at the default settings, except we'll choose to return the values in decibels. If we drag out of the band settings here and type make, you can see we've got a choice of 3 different types of setting. Each of these divides the frequency spectrum into different bands or regions for analysis in different ways. Let's have a look at the preset spectral analysis band settings first. The preset spectral analysis band settings has a number of presets that are configured to analyze specific frequency bands that are commonly most active for kick drums, snare drums, vocals or cymbals. And here you can also define the attack and release times for the analysis and the number of frequency bands within the defined range. If we set up a print string at this point, we can see the kind of ranges that these presets are working across. So we'll create a for each loop and we'll trigger it off of this custom event here, connect it to the print string. Now every time we get an event here, in this case it will be 10 times a second, this will return an array of sound submix spectral analysis band setting structures. Try saying that after a glass or two of pumpkin cider. So let's break that structure and see what we're getting. And we'll create a format text node so that we can read those settings in real time. So we're getting band frequency, I'll make that input A. The attack and release times are defined here, so they're not going to change. So the other thing I'm interested in seeing is the Q factor, and I'll make that input B. So let's have a look at what we get with this kick drum preset. So that's easier to see in the output log here. So with a kick drum preset using 10 bands, this gets us the magnitudes of a band around this frequency of 40, 43, 48, 52, etc. up to 91 Hertz. And you see the Q factor here is 10. So quite a narrow width of each band around these center frequencies. If we change the number of bands to 2, let's take a look at that. This time we've only got 2 bands and they're centered around frequencies 40 and 63, and the Q factor is much wider. So you can see that the system attempts to divide the given frequency range into the given number of logarithmically spaced bands, and sets an appropriate Q factor in order to limit the overlap between these. Let's set the bands back to 10, and we can see the snare preset gives us bands centered around 150 Hertz going up to 3000 Hertz, and the cymbals preset gives us 10 bands starting at 6 kHz and going up to 14 kHz. So we can see that each of these presets is designed to analyze the appropriate frequency ranges for the instruments. We'll look at the Make Musical spectral analysis band settings in a moment. For the Fireflies, we're just going to look broadly at what the music is doing. So we're breaking a wide spectrum range into just a few bands using the Make Full Spectrum Analysis band settings. With these settings, we define a minimum frequency, which I'm going to set at 100 Hz, and that serves as the center frequency for the lowest band, and a maximum frequency, which I'm going to leave at 16 kHz. And the number of bands I want to look at is just going to be 3. This spectrum is then going to be split evenly into the specified number of bands, with the central frequencies of each falling in such a way so that the uppermost band does not exceed that maximum frequency. I've recreated this in Reaper using some bandpass filters, so you can see that with our minimum set at 100 Hz, that's going to be our first band, and then we're going to have 2 more, one centered around 540 Hz and one centered around 3 kHz. Note how the Q factor has now automatically adjusted to a low value of 0.2, giving each of these 3 bands a wide bandwidth. We can hear what each of these bands sounds like if we add a bandpass filter effect to our submix. So let's find that submix, Tavern Music, and we'll add a submix effect preset, which I've made already, called Tavern Music Filter. It's a bandpass filter, and let's set that to 100 Hz initially to listen to that first band. So we'll find our music so we can solo it in a minute. It's that one there, and we'll play. So we'll just solo that. So that's what our band that's centered around 100 Hz sounds like. And then we can adjust the filter. And we've got another band that's listening to that range. And then our third band is centered around 3 kHz. So we're going to get the magnitudes of each of those bands and use these values to affect the particle system of the Fireflies. So now we've heard them, let's remove that filter. Now we've created the analysis settings, we can get the magnitudes themselves for each of those bands and read through them. So let's change this to band 0, band 1. Now we'll add another one for band 2. That can be input C. Now we'll get those 3 elements from that array using another for each loop. And we can use that array index to control a switch that's going to route each of those magnitudes to 3 different variables. Band 0, band 1, and band 2. And we'll connect those up to our format text so we can see what they are. Actually, let's use a tick to trigger that print string, and then we won't get the values just streaming down the page. If we set the print string duration to this delta time I just need to switch off that do normalize option there. So now we'll get the results in dBs. They're a little hard to follow, but hopefully if you look at band 0, you can see that jump that occurs on the first beat of each bar. 1, 2, 3, 1, 2, 3. Note how the numbers are lower when the magnitudes are high because they're in dB, so 0 dB would be the loudest. Now we've got those magnitudes for each band, we can use them to control the colours of the fireflies. So here's our firefly particle system component, and here's the firefly particle system itself. What we're going to be controlling is this colour over life using the parameter name particle colour. And you can see that we need to scale the values to a range between 0 and 1. So we'll get the magnitude of each band and we will map range clamped. Now for band 0 we're getting results between about 20 dB and 40 dB, and we're going to invert those, so we're going to map them to 1 and 0. Then we're going to use a power function here with an exponent of 3, so we get a relatively steep curve over the values in that range, and we'll use that to set color parameter of our fireflies, and that's particle color. And we'll split that struct pin so that we can access those variables. That will go into the R, the red. Changing the exponent value on a power function is a nice quick way of mapping input values to get non-linear outputs, as you can see here. Our next band, band 1, will do a similar thing. This time we'll map it over a slightly narrower range, and we'll use a different exponent on that power, 1.5, and that can go to green. And finally band 2, we get a slightly different range on this one, so that's going to be input 40 and 60 mapped to 1 to 0, and our power function here is going to be using exponent 2. This is all just to do with looking at the range of magnitudes we get from each band and then adjusting these appropriately to get the color effect that we wanted. So now we'll just connect those up here, and we can turn that off and we can see the final effect. Now one thing you'll notice is that because those bands are analysing the submix, you can see the colours and the way they change actually differs according to the amplitude of the sound, because obviously the amplitude of the sound on that submix is changing depending on how far away from the tavern I am. So at the moment we're sending the entire signal to this tavern music submix, and this takes into account the attenuation settings of the sound. Now there might be instances where you want to do this, but in this case the fireflies themselves remain at a constant distance from the tavern and the music playing inside the tavern. So having them respond to the listener distance or the player doesn't make a lot of sense. So instead what we can do is just have this sent to the master submix, which is the default submix, and we can route a second copy of the signal using a submix send. So here's one I prepared earlier, tavern music send. We'll use a manual send of level 1, and then we just need to make sure that the output level of that submix is set to 0 so that we don't actually hear that sent version. And then in the Fireflies blueprint we set that as the submix to be analysed. Now you should see that the Fireflies' response to the music is the same no matter the volume of the music itself as heard by me, the player. Let's look briefly at a couple of other settings on this Add Spectral Analysis Delegate node. The update rate we've mentioned already. That's how often to retrieve data from the spectral analyzer and to trigger the event. And that's in number of times per second with a maximum of 30 times a second. The noise floor is where you define the value below which you'll treat the sound as silent. And the normalize option normalizes the output of the band magnitudes between 0 and 1, outputting 0 dB as 1 and the noise floor as 0. The auto range system attempts to find the minimum and maximum values in the audio and to automatically normalize the values across this range. In other words, to treat the minimum as 0 and the maximum as 1. And you have attack and release values here to control how quickly that responds. Finally, let's take a look at the Make Musical Spectral Analysis band settings. If we find the blueprint called Scriabin, we'll just drop that into the meadow area, and we can see an example of the sort of thing that we can do with these settings. You can see that this is set up in exactly the same way as the Fireflies blueprint. We have a sound, in this case a piece of music, that's assigned to a submix, Scriabin submix. In the blueprint we have a submix variable that references that submix, and we've dragged out from that to create a spectral analysis delegate, which gives us this event here, and we've started the spectral analysis. The difference here is that the Make Musical Spectral Analysis band settings are specifically set up to create frequency bands that are associated with specific musical notes at a standard tuning of A equals 440 Hz. In tribute to the composer Scriabin, we've taken a melodic fragment from his piece Prometheus, the Poem of Fire. Scriabin was interested in the phenomenon of synesthesia, where people experience sensations in one sense or mode of perception in response to stimuli perceived by another sense. For example, one might experience letters or numbers as colours. In Scriabin's case, he mapped out relationships between musical pitches and colour, and we've attempted to recreate that mapping here. You can see from this notation that the melody starts on the note E4 and goes up to G-sharp 5. Using the Make Musical Spectral Analysis band settings, we've set the starting note for our bands as E4, and here we're creating an analysis band for each of the 24 semitones going up from this pitch. If the magnitude of any of our bands falls below 38, in other words minus 38 dB, then we set the color parameter to black, which has the effect of making the fireflies transparent. When the magnitudes are greater than minus 38 dB, we find which pitch is being played by checking through our magnitude array. Because we're getting values in dB, then the index of the array with the lowest magnitude value is actually going to be the loudest note. So this index is used to pick an appropriate color from our set of pre-made options. These approximately match Scriabin's original synesthetic pitch to color mapping. The debug section here also uses this index to give us the MIDI note name of each current pitch, its index and magnitude. So let's just turn that on so you can see the pitch to color relationships. In this video, we've seen how you can use the different band settings options of the Add Spectral Analysis Delegate node to create frequency bands in order to conduct real-time frequency analysis on an audio submix.